Just a brief announcement. I'm supposed to give a series of lectures starting at 4 o'clock, and the title is Machine Learning Flavors of Random Matrices, which in retrospect sounds to me quite technical. So just wanted to ensure, to let everybody know that actually it's just going to be very elementary and much less math and no exercises. So.
Hello? That's it. Yeah, okay. Okay, so not sure I'm going to be able to compete with that afternoon session. So my first, I just wanted to revisit this slide, and maybe a couple of points that people asked me afterwards threw up things that I hadn't clarified properly. I think the double sample trick, it really is a matter of just looking at those equations and convincing yourself that that goes through. As I say, the intuition is really that because the second sample is somehow independent of the choice of f, the probability that there's a very significant deviation between its true error and its error on the second sample is just small. That's basically what's behind it. This one, I think, maybe is more crucial, and that is where we're now using the fact that really all the information that we're conditioning on, that we're interested in, is relating to the performance of the function on the two samples, x and y. Here it's x, here it's y. And that enables us to move from a potentially uncountable number of functions to a finite number. And perhaps I didn't emphasize that quite enough. And I just want to illustrate it with maybe some linear functions just to show you that what is happening. So if you imagine, you've got a two-dimensional input space with some positive and negative examples. When you do that conditioning onto this is the double sample, I'm thinking, both the positive and, both the first sample and the second sample. Once you project, you're only interested in what the functions do on those examples. These two blue functions are effectively the same function. As far as the conditioning is concerned, they behave identically. So you can treat them as just a single function. Although they're different weight vectors, they behave identically on that sample. And this is where you're getting the contraction effectively of the function space to just a finite set of functions. Similarly, these two red ones, they behave identically. They do the same classification of all these points. And so they look identical as far as the actual probabilities that you're estimating are concerned. Okay, so that's what's meant by that step there, where we move from this case here, and we apply the union bound over the number of different behaviors that we can observe on that double sample. And that number is measured by this growth function, if you remember, 2m. That's actually the number of different behaviors on a 2m sample, the highest number. And again, somebody asked, is BH of 2m, BH of m the maximum? Yes. BH of m is the upper bound on. Obviously, for a particular sample, you may actually have fewer functions than that for a particular set of points. But BH of m is saying there cannot be more than this number of different functions on that set of points. Okay? So that's... and the other point that somebody raised is what happens if you consider the case where, BH of 2m is still the maximal, 2 to the m value. Can you get anywhere? And we'll see when we get to the end of the proof that actually, no, we can't. It ends up totally trivial in that case. It's only by, pumping in this sort of polynomial bound on the growth function that we actually are going to get a win and get a statistical result. Okay, so we're now in shape to go forward into symmetrization. This is the next keyword that you need at the cocktail party to impress people. Okay. Sorry?
We can go after
that. Okay, so yeah, we've had a few already, you know. Union bound, double sample, ghost sample. Okay, symmetrization. So now this is, again, a very nice, I think, trick. I hope you'll agree when I see it. It's not a substantially difficult thing to understand once you've seen it, but to come up with it, amazing. Okay, so if we consider a 2M sample S, since the points are generated independently, we're making this independent assumption of the way the points are generated, the probability of generating the same set of points in a different order is equal to the probability of generating that particular set. So say we had points x1, x2, x3. The chances that we actually generated x2, x1, x3 is identical. I mean, it's just we happen to get them in a different order. Okay? And that is true for any reordering of a set of sample points. Hence, consider now a set sigma of permutations. Some set. I mean, it could be the whole set of permutations, all permutations on m points. Could be some subset of those. And now we're going to do the following. We're going to generate a sample by first generating the sample in the normal way, independently at random. And then we're going to apply a random permutation from the set sigma. Okay, so we generate x1, x2, x3, xm. We randomly pick sigma from this set, capital sigma, and we permute them. And now that's our sample. So we have an ordering in the sample that we are considering fixed. Now clearly, doing that, we get a I'm going to call that probability distribution P superscript 2m sub sigma. Okay? Now, by the argument that those are equally probable, those different orderings, any event has equal probability under p to the 2m and p 2m sub sigma. Reordering that doesn't change the probabilities. Okay? So I'm writing this here, p2m of a is equal to p2m sub sigma of a, and we can write this as the effectively doing the order of choosing sigma first, so the probability of sigma of a, and then the expectation given a particular set of examples, and then the expectation over the double sample of that probability. So effectively what we're doing here is we're saying, yeah?
So what is the lowercase sigma distributed?
According to the uniform distribution. Sorry, the question was, what is this lowercase sigma here? That's right?
Yes.
So what I mean here is that I choose this lowercase permutation uniformly from this set sigma. And then I permute. I should have an a sub sigma probably here or something, which indicates that I permute the training set and then look at the event a on that particular training set. Okay? So this clearly is just a rewriting of this where we do the permutation after we've chosen the particular set of examples, and then we do the expectation over the choice of examples. Now, we're now going to apply this idea to bounding that last line here. Okay? So here we're going to try and apply this symmetrization trick. In other words, we're going to choose a set of permutations, and we're going to try and use that bound, which is using the permutation first and then the expectation. So the permutations we're going to be interested in are ones that swap corresponding elements between the training and ghost sample. So imagine you can take the first element of the training sample, first element of the ghost sample, swap them over. And that's one of the basis of the permutations. And then you can take the second and swap those and do any combination of those up to the mth. So there are 2 to the m possible permutations in that set, depending on whether you swap or do not swap each of the corresponding elements. Okay? So sigma has size 2 to the m. What happens? Okay, well, we just plug and play. here's that quantity we wanted to bound, and we write it as the expectation over the double sample of the probability, choosing a random permutation from that sec sigma, of the fact that the error of x is 0, error of y is greater than or equal to epsilon 2 for the permutation, for the permuted double sample, right? So what we're saying is, what is the probability when we do these permutation, this random permutation of the double sample, that this property still holds for a fixed, now we consider this is essentially conditioned on a fixed set, a double sample. And then we take the expectation of that over the choice of the double sample. So we fix the double sample, we consider permuting the elements. What is the probability that when we permute them by a random choice from this set, that we have 0 error on the left-hand side, on the training sample, and epsilon over 2 error on the ghost sample? Okay. So, essentially we're going to we can think of independently swapping these guys, and how many of those swaps can we do in such a way that we end up with all of the errors on the right-hand side. Okay, so there are overall, in the whole double sample, there are epsilon m over 2. This is an error rate, so because there are m in this second sample, the actual number of errors is epsilon m over 2, or at least that many. So there's epsilon m over 2 errors in this double sample, and in order for this property to be true, in other words, for this thing here to hold, we need all of those errors to be on the right-hand side. Right-hand side, okay? And because of the way we've chosen the set of sigma, we have essentially independently the probability of 1.5 of swapping those. Okay, so that particular error on this side and its corresponding point on the other side could be swapped. But we're not allowed to do that swap if we're going to keep this property that all of the errors are on the right-hand side. So effectively, that reduces the number of permutations that we can apply by 1/2 each time for each error. So the probability over this random choice is 2 to the minus epsilon m over 2, essentially 1/2 times to the power of the number of errors that we have on the right-hand side. So for each of those, I mean, you can do just a counting argument as another way of thinking of it. Count the permutations that actually leave those guys on the right-hand side. Well, it's all the permutations that do anything to the other pairs but don't change those set of points. So it's 2 to the m minus epsilon m over 2, and then divided by 2 to the m, because that's the total number of permutations. So that is then the ratio of the number that keep it happy with those that don't. Okay, and that is 2 to the minus epsilon m over 2, and the expectation of that, this is now independent of the actual set of sample points, so the expectation is certainly bounded. For every set of double samples, it's bounded by 2 to the minus epsilon m over 2, then certainly the expectation is bounded by 2 to the minus epsilon m over 2. Is that any questions on that? Yes. Okay, so the question was, if I got you right, was that how do the permutations affect the ghost sample, or the choice of the ghost sample, effectively? Yeah. Okay, so I think at the point where we start applying these permutations here, that's this point here, we've effectively forgotten in a way that there was a sample and a ghost sample. And what we're thinking of doing is randomly mixing points with the ghost and between the ghost and the true sample, sort of interchanging. And we're saying, okay, because of the way the probabilities stack up, it shouldn't make any difference if we swap those two. But we find out that there's a significant number that we aren't allowed to swap, because if we did, it would actually invalidate the conclusions that we were drawing. And so we're working out the fraction of those which invalidate and saying, okay, the probability then is bounded by that fraction. Okay. Effectively what we're saying is that the errors, if there are a lot of them, it's weird that they're all on the right-hand side. That's weird. It's unlikely, because this is an even training set. It shouldn't be that there are all those errors on the right-hand side, and that we're bounding the likelihood of that event. And this is just a technical way. Symmetrization is a technical way of sort of making that intuition sort of formal. Is that okay? Yeah. Any other questions? Okay. So the trick again is just to consider this probability that the event holds under these random permutations where we swap corresponding elements, and we note that in order to have this hold, all of the error elements have to stay on the right-hand side, and since there are epsilon m over 2 of them, the probability is 2 to the minus epsilon n over 2. That's basically it. Okay. But now we're really there. Okay, so this is the kind of thing we like, an exponential decay in probability with the sample size. Okay, this is looking really good. And so now what we can do is set this equal to delta over 2 BH of 2m, which was we're now back to putting the whole thing together. Effectively, that 2 BH of 2m is here. What we want to do is to make this less than delta. So we're going to make this quantity less than delta divided by 2h bn. Then we can invert that to give a bound on epsilon. So if you want to spend just 2 minutes trying to do that, so just set this equal to that and invert it where we know what this BH of 2m is from Sauer's lemma. So if you've just got that down there, I'll go back to Sauer's lemma. There's Sauer's lemma. So BH of m is less than or equal to this quantity, with VC dimension d, em over d to the d. So you can plug that in place of this, set that equal to that, and solve for epsilon. Okay. Just give you 2 minutes. Okay. Yeah, Lorenzo. Yeah.
The probability of 2m on sigma to the expectation previous. If the probability under e to power 2m or
Yes.
permutation as well are the same. But then you can from the probability to the expectation.
Well, it's the expectation of the other probability, so that's why. You're saying that's the thing you're not sure. Is that right? Yeah. I mean that was. Sorry. Yeah. I mean that's essentially this thing here, right? Okay. So I mean Yeah.
And the first, I see the first equality.
Yes, that's. I mean, this is just another way of writing this. Essentially, it's not a. I mean, it's just notation, really. It's just saying what we're doing is working out the probability under the sigma, and yeah, I mean, it's the expectation of that is yeah. Okay, the same. Yeah. Yeah. Yes.
Why do you need symmetrization outcomes? I mean, I think you can go from the first time.
From here to here. Can you? I don't see how you do it directly. So the question was, can you go directly from here to here, right? That was the question. Or rather, yeah. So, sorry, from here to here. Yeah, I mean, in a way, that's all symmetrization is doing, is formalizing the independence assumption, I guess you could say, yeah. Yeah. I mean, it's just saying that the likelihood of all of the things happening in the second half is sort of weird, yeah. But yeah, it's just a formal way of writing that, yeah. Okay. Yeah, sounds good, yeah. Okay, how many people have succeeded there? Is that, yeah? I'll just put up a derivation here to show you how it works. So basically you're setting that 2 to the minus epsilon m over 2 equal to delta over 2 bh of m. Take log to the base 2 on both sides. And multiply through by minus, and you get epsilon m over 2 here, and log of the inverse ratio here, 2 bhm over delta. That's because of the minus going through the log. Then you put epsilon is 2 over m, and substituting in, sorry, this should be 2m, shouldn't it, here? There should be a 2m. It should be a 2m. And then substituting in Sauer's lemma, well, firstly separating this as the log of a product into the sum of the two logs, log 2 over delta and log bh over m, and then substituting in the Sauer lemma bound, which is 2em over d to the power d, and taking the log of that, the d comes down, and you get d log 2em over d. Okay. So again, it's just a manipulation of the formulae. Is everyone happy with that? Okay, I just wanted to give you a chance to throw some figures around. So there it is. So what that tells you, and this is, if you like, the central result of learning theory in some sense. Sorry, there it isn't. There it is. It says that that's the formula as we had it. So with probability at least 1 minus delta, the generalization error of a function h in a class h with VC dimension d, which has 0 training error, is bounded by the following quantity: 2 over m, d, the VC dimension log 2em over delta, plus log 2 over delta. So notice again the same form that we've been seeing coming out repeatedly. The inverse dependence on m. So as the training set size goes up, you're getting a decrease in the training error. the log 2 over delta, the delta coming in very benignly under the log. In this case it's log to the base 2. Last time it was natural log, as I remember, but not much in it. And now this complexity term, which if you remember before we had log 1 over q n, where we'd chosen this prior sort of weightings of the functions, is replaced by this uniform term, which is equal for all functions, and it's d log 2em over d. So you can think of d in some sense as measuring the complexity of the function class. So the VC dimension is some nice measure of the function class. And notice that the polynomial growth that we had directly translates into this logarithmic growth here in the sample size, and we're setting that against the inverse m, which is what is controlling the generalization error. So provided we take a sufficiently large sample, this is going to be dominated by this m term. This is already quite small, and we're going to get a good bound on the generalization. Okay. If, on the other hand, we'd applied the result where we still had exponential growth in the growth function, then this would have been log of 2 to the 2m. Take the log of that and you just have 2m, and you get the m's cancel and you get a trivial bound. So you do need that significant decay of the growth function below the exponential growth in order to get an effective generalization. So this, as I say, was heralded as a very sort of key result, and it's very nice in the sense that it characterizes learning in the following sense, that there are lower bounds. Again, I'm not going to go into the proofs of these, but there are lower bounds that say that given a class of VC dimension D, there exist distributions such that with probability at least delta over m random examples, the error of H is at least this quantity. So it's a sort of inverse in the sense that it says, there are cases in which you can do as roughly as badly. I mean, okay, there's a log factor missing here, but log factors between learning theorists don't count for much. So there's the d log 2em over d here, and here there's a d over m, but and the constants are a bit different, and there's the but apart from that, I mean, this is very, very close lower bound. So in a sense, what this is telling us is that the VC dimension is actually the right characterization of learning in this classification sense. So it's a very nice sort of closed theory in that sense. It all looks very beautiful. There are corresponding results for non-zero training error, which the techniques are very, very similar, but it just gets a little bit more messy, and I wanted to try and give you the flavor of what's going on here, so I'm not going to go into this at all with non-zero training error, but you can get a similar type of result which says that the bound on the generalization is the number of this should be k over m, sorry, this is a mistake. K is the number of training errors, so k over m, so that's the empirical training error, plus a term that looks very much like what we had before, except that now there's a square root involved, which makes it larger and looser, and that comes from using different bounds on the probabilities that you need in the non-zero training case. In fact, the Pack-Bayes bounds that are now being developed have sort of interpolate between these two. So, you could expect that as you go towards low training error, you might actually get something better than this square root. The square root is needed definitely when you have training errors that are large, but there is something that goes between those two. Okay, we're going to see the square root come back in the Rademacher complexity tomorrow when we look at the bounds that come out of the Rademacher complexity. So I wanted to just show it you here. Why is the square root bad? Because these things should be very much less than 1. If you take the square root of something less than 1, it gets bigger. quite significantly. So it's not a good thing, but it's still an interesting bound. So that's the non-zero training error case. So now I want to sort of step back and sort of review where we've got to, and in a sense, the good news is that this looks like a really nice theory. It all ties together. You've got lower and upper bounds. It's a beautiful sort of proof and so on. The bad news is it doesn't seem to actually apply in practice. It's an interesting case. The problem is that you can't criticize it as it stands. It's clearly correct. We've got upper and lower bounds. But it doesn't apply. And there's this clear mismatch between the theory and the practice. And probably the best example of that is the support vector machine. Okay. So this is a sort of, if you like, a catastrophic failure of systemic failure of the pack theory. So what do SVMs? Well, from the sort of learning theory point of view, all they are is applying linear functions in very high dimensional feature spaces. Okay, there's the kernel trick that you've learnt about from Berder and so on, which allows you to do this efficiently. But from a point of view of the learning theorist, how you actually implement that function is irrelevant. You're actually using a linear function in a very high dimensional space. Now we know that the VC dimension of a linear function space is the dimension of that space. So the VC dimension of these SVM spaces is very high, and there's no way that the theory will give anything like an indication of a good bound. I mean, for instance, if you use the Gaussian kernel, the feature space is actually infinite dimensional. So you're actually into that bound, and clearly that's not going to give you anything non-trivial. So the pack theory is completely failing to give any indication of why these functions should work at all. And if you were just using the pack theory to guide you in your investigation of learning algorithms, you would throw out SVMs immediately. And yet we all know that they actually have very impressive performance. So how do they work, and what's happening? And we need to, learning theory needs to sort of wake up and somehow understand what's going on and try and analyze this. So this was the state of the game, if you like, in about 93-4 when SVMs had been invented and learning theory was still stuck with a pack VC dimension. Okay. SVMs work in the following way. The one norm SVM seeks to minimize this 2 norm of the weight vectors plus the 1 norm of the slack variables, where the slack variables measure how much the particular training example fails to be at margin 1. So it effectively is enforcing a margin 1. The actual geometric margin is effectively maximized by minimizing the weight vector here, and these slack variables allow individual points to fail to meet that margin, but it penalizes those failures by adding in this 1 norm of the slack variables to the minimization. Okay, so that's how it works. And the intuition behind SVMs, so I mean they weren't invented just arbitrarily. I mean there was a very clear intuition that maximizing the margin would make it possible to obtain good generalization despite a high VC dimension. And the phrase effective VC dimension was thrown around, but was an imprecise. There was no precise definition of what that meant at the time. Now clearly, so how are we getting around this lower bound? I mean, we've got a lower bound. Can't do better than the VC dimension. What's happening? But there's a critical difference between the upper bound and the lower bound. The upper bound says for every distribution, you're going to have better performance than the VC bound. For the lower bound says there exist distributions for which you are forced to make this error. So what we're effectively using here is the fact that the distributions you meet in practice may not be as nasty as the worst case distributions. Effectively, we're looking for something, if you like, a benign distribution, something about the distribution which is serendipitous. It's helping us. Nature is actually not against us. It's helping us in learning the actual task that we're trying to learn. And in fact, what we find is that the margin is, in a sense, a measure of how lucky we are in the particular distribution that we're looking at. The distribution is somehow luckily aligned with the hyperplane that we need to separate the data, and actually is, if you like, showing us the solution. And that is what is actually occurring in order to avoid the difficulties of the lower bound. So we know that the lower bound will tell us, yes, if you use these high-dimensional spaces, there are distributions that will mess you up. That's for sure. What we're saying is that the margin is telling us, actually, that we can measure the benignness of the distribution as we do our training, and we can effectively see that we're in a lucky situation. So what I'm now going to do is sort of take the first approach to proving the bounds for SVMs, which are based on the margin. I won't give a complete proof of these, but I'll give a fairly... It follows a very similar pattern to the proof for the that we've seen so far for the VC dimension. But I want to give you the flavor of how these ideas are translated across. And then tomorrow we'll again look at a very different approach. Well, not very different, but the Rademacher approach, which has a slightly different flavor and also provides bounds for SVMs. So I guess maybe there's a little bias in the way that I'm presenting things in favor of SVMs. Certainly I will mention bounds for boosting tomorrow as well. And what I won't do is talk about bounds in terms of sparsity, which I think is a serious omission, but unfortunately, there just wasn't time to fit it in, I'm afraid. But that would be, if I was to name the big missing thing, I would say bounds in terms of sparsity would be it in this set of lectures. And I don't think Olivier is going to talk about those either, unfortunately, but okay, that's life. Okay, so next big sort of idea, covering numbers, okay? I don't know what you might think this might mean, but you definitely want to throw this one in when you're chatting about learning theory. Okay, have you thought how large the covering numbers might be? That sort of phrase would be good. Okay, so covering numbers are going to replace the growth function, right? Remember, the growth function was sort of measuring how many different things we could do on a finite sample. The growth function is going to do the same thing. The covering numbers are going to do the same thing, but they're going to do it for real valued functions. So now we don't have just a finite set of possibilities. With the binary functions, we just had +1, -1. So we knew there were only a finite number, and we wanted to just find out how many fewer there were than 2 to the m. Here, we don't have that possibility of a finite number. But what we're going to try and show is that if we're only interested in accuracy of a certain amount at each point, then we can get down to a very small number. So rather than be interested in precisely what happens at each training point, the precise value of the function, it's a real valued function, we're going to say we're happy provided we can find a function that's within some measure gamma, and that's this gamma here in the thing here. Measure gamma accuracy to the output. So we can find something that's within gamma of the right value. And then the trick will be that because the margin gives us a little bit of freedom in, we're going to still get correct classification if we got a margin of gamma, we're going to still get correct classification if we move the value of the output by less than gamma. That gives us this sort of leverage that we can substitute all the functions by this sort of subset that are only accurate to within gamma, and there's a finite number, and then we can apply the union bound again. So it's a similar trick. It's just a little bit more machinery that we have to bring in to actually do it. Okay, so bear with this definition. This is the definition of the covering numbers. So what we are interested in now is a function class f. Well, it could just be any set of objects here at this point. Some norm on the functions, which measures the difference between two functions. And we're going to say this covering number is the size I should have here of the set U gamma, such that we can find in U, for any function in f, a representative in U which is within gamma distance to f. So if you think of maybe I'll draw a diagram on my thing here to illustrate this. So if you think of your set of f points here, what you're effectively doing is trying to find a sort of sub grid or set of these points, such that any point, this is the U gamma set, right? This is the whole set f, and the finite set is going to be the U gamma. And what you want to have is the property that whatever point I now choose in f, so here, I can find a point in U gamma which is closer than gamma to that f. So effectively, if you put balls of radius gamma around these points, they cover the whole. I have to draw them a bit bigger to make it work, but you see what I mean. It covers the whole of the space, right? So that's why it's called a covering, because you're covering the space with these balls. In the way that I've indicated, and the interesting, yeah. This would be a covering. It's usually referred to. U gamma is a covering. The covering numbers are the smallest size of set, the smallest size of that cover set.
You're heading for a countable covering, or a finite covering, or what?
Definitely finite. It's the same trick, in the sense we're going to apply the union bound at the end, so we want to end up with something that's finite. Yeah. Okay. Did everyone hear that question? Yeah, everyone was happy with that? Okay, good. So yeah, covering is putting these balls to cover the whole thing, and the covering number is the smallest. Obviously, how you place them is going to be quite critical to get the coverage. It may be very hard to find the optimal set of way to put them, but we want to find a bound on the smallest number that we need to cover. Yeah, again, question here. Yes.
So, is that sort of limited square that you've drawn supposed to be, where do you get the extra limitation from? Do you have a bound on the creature you're drawing? Is that supposed to be actually meaningful, or is it just you want to draw something? Small.
It's just that is just meant to represent some set of functions in a geometrical way, but it doesn't mean anything that it's square, if that's what you meant. No. I didn't understand.
In that situation, there might be an unknowable number of points in that region.
Absolutely.
If the region itself is bounded,
yeah,
then you can get this finite covering at the end. I was asking if that was something you're meaning to have included in that figure. I can ask after.
Yeah, I guess in a way, yes, is the answer. You're thinking of, is it compact, really? Is that the question in a way?
I can ask.
Okay, we'll ask later on. Okay. Sorry, I didn't quite follow. But yes, if you're in compactness, there's this thing that if you have a cover, there's a finite subcover, always. So it's very related to that idea. This is a finite subcover we're interested in, and we would expect it to be compact in that sense. So yes, I think the answer is probably yes, what you were answering. Okay. Okay, so that's the general definition. We're actually interested in this following gamma growth function, where we've now substituted a particular metric here. So this is the covering number, and we've got a particular metric which is the L infinity metric on the sample. By what we mean here is that we look at what the functions do on the training points, and we say we're interested in getting so we've got a general function, and what we want to ensure is in our cover there is a function which on all of the training points has output within gamma of. So this is our way of measuring the difference between two functions. We're saying that two functions are at a distance epsilon, let's say, if the distance between their outputs on all of the training examples is less than or equal to epsilon. And on one of them it's equal to epsilon, let's say. So what we mean by a cover now is if we've got an element, let's say we pick a function f, we pick the closest element in the cover, then that element, that function, will have an output within gamma of the function that we started with on all of the training points. Not on other points, don't worry about them, but just on the training points. Okay? So that's the thing we're interested in, and we actually are interested in how bad this can be over choices of training sets. So again, it's a bit like the growth function where we could think of it as defined in terms of a particular set sample, but we were interested in the worst case, the highest value of the number of functions that we could get over all choices. Okay? So, it's a bit hairy, but if you keep that intuition, we're just trying to find a finite set of prototypical functions that, any function we care to choose, we can find one of them in our set that's pretty like it, and what we mean by pretty like is on the sample, it's within gamma in its output. Okay, so this all relies on having real valued functions, of course. Functions that give a real value output. Okay, so now we're in shape to basically rerun our previous approach exactly. You'll see that we're going to follow the same strategy. Oh, geez, we should be having a break, shouldn't we? Yeah, okay, we'll take a break. It was just such fun, We'll meet back at 20 past. Okay, so quarter of an hour break, and we'll come to this.
What he was asking was if the space of function is infinite, how can you cover it? And I think the answer would lost that those functions that are far away from those points would give the same result on the points, so that that limits the space of functions. That's why you can cover them.
Yes, that I think, but I think also he's right in that. Thanks. I think he was.